Hello everyone and welcome back. So in this video, I just want to introduce the concept of thermal resistance. So far, I've introduced to you the three modes of heat transfer, which is conduction, convection, and radiation. And we've seen that in all of these equations that we've looked at, the equations depending on delta T, which for Fourier's law, dt over here is the temperature difference between both sides of the wall. And for convection here, the temperature of the surface minus the temperature of the moving fluid. And in radiation, it is the fourth power temperature difference from the surface with the surroundings. So as you can see, in all of these cases, there's a delta T that is involved. And so the thermal resistance concept depends on being able to express the heat flow equation with Q equals the delta T over a resistance value. And this resistance value is a quantity that we call thermal resistance, and it would take obviously different forms depending on which mode of heat transfer we're talking about. Because as I showed you earlier, if you're using the Fourier's law or if you're using the Newton's law of cooling, you would have a different expression with how you'd express the heat flux and therefore the heat flow. So what we're going to do now is we're going to look at what the thermal resistance expression looks like for both conduction and convection modes, because they're the ones that are extensively used in practical examples in heat transfer calculations. So if we look at conduction, now let's just focus at conduction, then we're going to look at convection. We start with the Fourier's law because that tells us how to calculate the heat flux. And we know that the heat flux in Fourier's law, it's a -1 multiplied by the thermal conductivity of the material multiplied by the temperature difference, so T2 minus T1, over the length of the wall. Now we can rewrite that as -1 times thermal conductivity times delta T over the length. This is just me simplifying it. And we know that the heat flow equation, so the heat flow is the heat flux multiplied by the area. And so looking now at this heat flow equation and looking at the thermal resistance heat flow equation that I just showed you, we can figure out what the thermal resistance would be. So in terms of conduction, the thermal resistance must be the length over the thermal conductivity multiplied by the area. And so if you were going to use this equation for a conduction problem, then the thermal resistance that you would use would be the length over thermal conductivity times area. Now, let's say you have a convection problem and you still want to use this thermal resistance concept. So you want to express the heat flow using this equation. So let's try to see what the thermal resistance then looks like. So let's start with the same fundamental equation. And for convection, it's Newton's law of cooling. So you have the heat flux is equal to the average convection coefficient multiplied by the temperature difference of the surface minus the temperature of the bulk of the fluid. And what we can do over here is we can express the temperature difference as the delta T. And if we want to find the heat flow, we know that we just have to multiply it by the surface area. And so now if you compare this heat flow equation with the thermal resistance equation that we're trying to get at, you'll see that the thermal resistance of the convection would be 1 over the heat transfer coefficient, so 1 over the average heat transfer coefficient multiplied by the surface area. And this is good to know because we might be using it in example problems together. So nothing on your end to do, it's just an awareness that the heat flow equation can be represented like this. And if you were facing problems that require or give you thermal resistances, I want you to be able to back calculate for what the heat transfer convection coefficient is if it's a convection problem, or I want you to be able to back calculate for the thermal conductivity if you were given the thermal resistance of conduction. And then from there, you can calculate what the thermal conductivity is if you need to. So I'm just opening your mind with different relationships that do exist, and sometimes you might want to utilize the thermal resistance concept to help you solve problems more efficiently.